Look forward to your talk.
I'm also an associate professor at KTH and CEO of Logical Clocks. If my slides come up. There we go. All right. So I'm going to talk a bit about platform support for deep learning. So if you have a data science team and you want to make them more productive and you want to know kind of what people are doing at the hyperscale AI companies, I'm going to talk a bit about how you would get there. And it's going to be a lot about technology, so platform support. So we had a really nice talk by Timothy there. He talked about how he used a labeled training data set to make a very nice model for predicting option prices. And we know that if you have a large labeled data set, you can solve a lot of prediction problems in finance. If you're lucky enough to have that nice large labeled data set. Because a lot of the problems are, of course, nonlinear, and deep nets are good for that. So the interesting observation we've seen a lot in the deep learning community is that as you have larger and larger labeled data sets, at some point you're going to outperform the handcrafted traditional machine learning algorithms. This is quite a well-known diagram. Many of you have seen this before. If you have small labeled data sets, you can use domain-specific knowledge to outperform deep neural networks. But as that data volumes increase, then we begin to outperform the traditional machine learning techniques, things like random forests and gradient-boosted decision trees. So where we are now is that we've been collecting larger and larger data sets. We have technology for storing big data, managing and processing big data, and that's just going and growing and growing. We know that the volumes of data out there in finance and in other industries just keeps on increasing. So this trend towards more and more deep learning will continue in the near future. Now, if you have larger and larger data volumes, the question you have to have is, well, do I need more compute? And the founder, or father, I should say, of reinforcement learning, Rich Sutton, he basically said that methods that scale with compute are the future of AI. Right? And those of you who know RL know that it completely doesn't scale with compute. It's single-threaded. Right? Okay, so let's have a look at an example of that. Last year was kind of a watershed moment. Facebook released a paper where they showed that they could reduce the time for training a very famous data set called ImageNet from 2 weeks, if you have a single GPU, to 1 hour. Now, that time of 1 hour to train that very large data set with 1 million images, I think Google recently said it's 25 minutes. So this trend towards reducing the amount of time it takes to train large networks on large volumes of data it's part of the core DNA of the hyperscale AI companies. So if you're working at Baidu or Google or Facebook, you have access to these thousands of GPUs. You will be a lot more productive in training your models. You'll be able to train them much faster and get your ideas out there and tested. Now, training is just one part of working with deep learning. The other part, the main part, is actually doing experiments. So you have an idea and you say, well, you know, I'm going to build a model. I don't really know where to start, so I'm going to run a lot of experiments. Now, the way it's happening at the hyperscale companies now is that they're actually automating a lot of that, right? So rather than designing your multi-layer convolutional neural network, why not have a system that learns it for you by running lots of experiments in parallel? This is a reference from a paper that came out last week. Google beat the state of the art in both ImageNet and in CFAR10. And they did it with lots and lots of compute. So you can see in bold letters there's 450 GPUs in 7 days. This is what we call weak scalability. You can run lots of parallel experiments on your 450 GPUs. They don't need to talk to each other. They're basically going to run a different experiment. And then they use, in this case, genetic algorithms to find the best potential solutions. And then they generate new population for the next run. And then you let this run all by itself. So if you think of deep learning as being an inner loop, where you're training a deep learning network, you have an inner loop, there is now an outer loop. And the outer loop is hyperparameter optimization, where you run many experiments, you run them in parallel, and you try and establish good hyperparameters, which you can then run in large-scale distributed training networks. That's basically the state of the art as to where we are today. So what this means basically for you as a data scientist, you don't want to have Google envy, right? You don't want to be sitting there with your 1 GPU thinking, it's taken me 2 weeks to train this model. So if you have distributed deep learning for both experimentation and for training, you will get more productive. I mean, orders of magnitude more productive. You'll be instant gratification would be one way of looking at it. But more, I would think of it as being you get interactively, you can design better models and train them in much quicker time. Okay, so where we are with distributed training, well, look at training first because experimentation is slightly different. If we have a single host, you could buy an NVIDIA box, a DGX1, which has 8 GPUs on it. As you have, if you're working with just a single host and you're not doing distributed training, you're going to reach a plateau. And if you're doing ImageNet and training that, the plateau will be about a day. You won't get trained in faster than a day. Facebook, we saw, we're down to 1 hour. Google down to 25 minutes. Distributed will enable you to use available compute effectively to reduce your training time. And where we are today is that we've just started on the journey, right? So really the Facebook paper was a watershed where people said, hang on, they are really training terabyte data sets in 1 hour. And in 2018, we're going to see a lot more of it, and in the future, we'll see even more. The problem with distributed training, if you get into it, is that in theory, it should just scale out with compute, but in practice, it doesn't, right? So distributed training itself, you can either follow an asynchronous stochastic gradient descent model or a synchronous blocking one, and typically people are using synchronous. Google had a very influential paper where they showed that the synchronous model could scale quite well, but also it had better convergence guarantees, and in the end you want to have more accurate models. So in practice, adding more compute won't always make you go faster. And then the bad news for this is that if you're working with TensorFlow, the TensorFlow architecture for distributed training is based on something called parameter servers. And parameter servers, they end up being a bottleneck. And what the big boys are doing is they're running what we call Ring-AllReduce algorithm. They're building high-performance computing hardware where you're using InfiniBand networking. We'll see in a second that you set up your nodes in a ring. It's bandwidth optimal. And the state-of-the-art algorithm for distributed training right now is Ring-AllReduce. And I'll just show you what it looks like here so you get a visual kind of intuitive understanding for it. On the left-hand side, as you're looking at it, you'll see Ring-AllReduce, and on the right, we have the parameter server model. So in Ring-AllReduce, what happens is that we're going to have a batch which comes in, and each GPU will take, it's this data parallel training, I should add. So each GPU is taking a subset of the batch, it's going to compute the gradients, and then it's going to send them to its neighbor. And it's going to receive its gradients from its neighbor as well. And there are a lot of optimizations. So for example, when you're doing the backward pass after you've computed the gradients in the first layer, you can broadcast them. And then they get aggregated in the reduce step. On the right-hand side, we can see, or your right-hand side, you can see the parameter server model. In this case, you have either a central server or several servers that aggregate the gradients on each iteration of synchronous stochastic gradient descent. You can have several of them, but the GPUs themselves, they're not using all of their available upload and download capacity. So they're basically just using their upload capacity to send up, and then they download, but the ring-reduce model is bandwidth optimal. So in this case, the reason why we care about bandwidth is that is the bottleneck for distributed training. I am Irish, and I do, you can say basically that the gradients flow more freely, like the Guinness on the left than the one on the right. Okay, so that's a cliche. So let me show you some figures just to convince you. These aren't my figures, these are from Uber. Uber have a platform called Michelangelo. It's very interesting with distributed training. And I've highlighted just one number because it's really the only one you need to look at on this particular slide. It's in yellow, and you can see 0.7x for one, and the other one is 40.7x. So that's the speed up in throughput. So 0.7 means it actually went slower. So 1.0 would be the same speed. So with 64 GPUs, we can see that this architecture, VGG16, which is quite a dense network, that means a lot of gradients need to get sent to your neighbors when you execute an iteration. And that's a dense network. A lot of network traffic will be sent out, and the parameter server model just didn't scale. It went slower. So with 64 GPUs, it went 0.7 times the speed of one GPU. However, Horovod, which is a library that Uber have developed, it's open source. You can go ahead, download it, use it. They got a speed up of 40x. So parameter server models don't scale. There is a solution. The Horovod is not the only Ring-AllReduce algorithm out there. There is also one by Baidu, which is in TensorFlow Contrib. If you're using Cafe 2, there's good support there, and if you're using CNTK, there's some reasonable support there as well. PyTorch, unfortunately, doesn't really have much yet in terms of distributed training. So what the hyperscale AI companies do when they want to train on tens of GPUs or hundreds of GPUs is they'll actually send the gradients when you're doing your aggregation over a separate network. So in this case, they'll send it typically over an InfiniBand network. So the experiment results reported by Facebook used 2 56 gigabit network ports per server. That's 112 gigabits of aggregate bandwidth per server. And they'd have a separate Ethernet connection for reading the files in and writing the checkpoints out, because you don't want those two to interfere with each other. The problem with synchronous stochastic gradient descent is that if you get just one node going a bit slower, or one network link going a bit slower, or even one internal bus connection between two GPUs going slower, that will slow down training for all of the GPUs. Okay, so this is the architecture level. Show me the code. Show me the money. What's it look like? Hopefully you can read this. This is pretty straightforward. So this is TensorFlow code in Python. It's on Horovod, and it's on this platform called Hops. So we have a platform, an open source platform, a Hadoop platform, which supports TensorFlow, and it supports Horovod. And this is the code you would write to do distributed training with Horovod. Basically, you have, we start at the top, you import Horovod, you just need to call init, and you wrap your optimizer. So if you're using Atom optimizer, you just wrap it here in Horovod, because that optimizer will then broadcast the gradients for you. And then you can have maybe one particular node which is going to save the model and checkpoint, and then the rest of the nodes can run the basic TensorFlow code. So you just put your ordinary TensorFlow code in here, and this code can all be run from a Python notebook. So it's not actually that intimidating. If you've looked at distributed TensorFlow, it's a much nicer model. The other alternative is to training. The other reason why it's useful to have a lot of GPU resources is because you want to do experiments in parallel. And if you want to do experiments in parallel on our particular platform, it's as simple as the following. You define a model function here, and as parameters, you define the as parameters to that function, you have your hyperparameters. So in this case, we have 2 hyperparameters, a learning rate and dropout. If I wanted more, I just add it as a parameter there. And then we have this piece of code down here, which would be typically in a separate paragraph in your notebook. And in here, we specify the hyperparameters as a dict. And then we just call our function with a dict. And what happens when we call this function here is it's going to start 6 different processes out on the network. This is actually using Spark, Apache Spark, to actually start these as executors. They will get some GPUs. When you launch it, you decide how many GPUs you'll get, and then it will execute the TensorFlow code in here. So this experiment.launch will launch our executors in the cluster, and then we'll have 6 executors running. And what we get out of it, this is incredibly ugly. I look at it here. You can't really see it, but in your tensor board, you can just then visually look at it and say, okay, well, I can see that this point at the top, which had this learning rate and this dropout rate, gave me the best prediction accuracy. And then if you want to train that on a very large data set, you can do distributed training with Horovod. So that's the typical way in which people will work on a platform such as ours. You'll do hyperparameter optimization, a lot of parallel experiments, and then when you're happy enough with that, you go to distributed training on larger data sets. So the question is, if you're going to do this, you can go to the cloud and get GPUs. You may be running on-prem, and you need to buy some GPUs, and the question is, what do you buy if you're going to go on-prem? For the same price, you can buy an NVIDIA DGX1, or you could buy 100 GPUs. Now, in our research lab, we bought these 100 GPU things, right? So what we can see in practice is that for convolutional neural nets, in any case, the training performance of one of these servers, which costs 1/10 of the price of this, is about 60-70%. So for 1/10 of the price. Now, the reason why it's good to have more GPUs than fewer is because if you have a team of 5 people and you have 8 GPUs, it's very hard to do parallel experiments. It's very hard to share those effectively between people. Data scientists want a lot of GPUs in order to do experimentation effectively. So these two cost the same currently at like market prices, and what we do in our particular platform to make them available is we have a version of Hadoop called Hops, and it supports GPUs as a resource. So you can ask the platform, I'd like to have 4 GPUs, and I don't care which host they're on. So I'm doing parallel experiments. Or I'm going to do distributed training. I'd like 100 GPUs on 10 hosts that have InfiniBand. And the take-home point here is that if you're going to buy a bunch of desktop machines and put 2 GPUs in every desktop machine for all of your 5 data scientists, so you now have 10 GPUs, how do they use the 10 GPUs? I mean, do they log into their neighbor's computer? I mean, this is not the way it should work, right? Your GPU should be a managed resource that is available to all of the team. So this is something, you'll find this on I had an O'Reilly blog post on distributed TensorFlow where I published this, but basically you can see that we're getting near linear scaling on this commodity server box with the 1080 Ti cards. So if we talk to people and say, well, what kind of advice do we have if you're half on-prem at a cloud shop? Well, basically, if you have a base GPU load where you're doing experiments or you're doing workflows that run periodically and you have them run every day or every hour or whatever, you will typically gain a lot by running that on premise. And then your variable load, you can put it on the cloud. That would be a cost-effective way of setting up your data science team. Just a little figure about that machine. I think the machine itself pays for itself in about 11 weeks or 12 weeks compared to using a P3 8x large in AWS. So that's distributed training. We have a platform, like I said, that not just does the hyperscale data science, but it also does security. So we have a nice model. It's called Hopsworks, and the platform itself is the world's fastest Hadoop distribution. It's 16 times the speed of normal Hadoop. It supports GPUs. But the platform itself has lots of services. So things like TensorFlow, Spark, Flink, Jupyter Notebooks are common. And you can do model serving, training, and testing all on one system. So the abstractions we introduce to work that are particularly of interest to people working with sensitive data is that we introduce a new concept, something called a project. And what a project is a grouping of users and data. So if you have some sensitive data that you need to protect, you can basically group it in a project. It's like a sandbox. And then only these 2 users can access those 2 blue data sets, topic and shared topic. And if I have another project, this is a different project with 2 other users and 2 different data sets, or one overlapping data set, the shared topic. And you can have, of course, projects where everybody is a member of the project. So this is quite a user-friendly, I would say, understandable security model for people to work with. And just to give an example of how this kind of thing is used, imagine you have some FX data stream coming in, and you have some engineering people who are going to clean it up and make it available to an FX project. What would happen is that data may come in via Kafka to a topic, and you would maybe put it into a historical database like Hive for historical analysis, and you might put a live version of it in so that they can do real-time streaming analytics on that data as it comes in. The FX team are now free to manage that particular project as they wish and add people to it and remove it and do their interactive analytics on it. So what we also support, because we have these nice concepts of projects, is that each project can have its own Conda environment or pip libraries they can install. This is quite unique in Hadoop, and it's an absolute must in the Python world. And as a whole, what you end up with is an architecture where you can run TensorFlow as your center point with TensorBoard and TensorFlow serving and experiments and Kafka and Hive and so on. We do model serving as well, so you can click and run your models, and then they're available as TensorFlow serving servers with GRPC API. And we do have an API to make this easier to use, right? So you've some support for doing parallel experiments like we saw. We also have neural architecture search and managing TensorBoard and HDFS. So just to conclude, what I talked about was distributed deep learning, and distributed deep learning is coming. You may be, I don't know where you all are on this pyramid, but I expect within a few years everyone will be up at the top of the pyramid. So it's a question of how long it will take you to climb up there. You can buy a DGX1 and end up here, but really to get benefit you need to start doing things like parallel experimentation above all else. Distributed training will come as your data sets grow and grow, which they inevitably are doing. If you want to read more, there's a blog post. We have a website. This platform is, we have a company behind it called Logical Clocks. and you can contact me if you're interested. And there's a big team behind this, and a lot of people have contributed to this particular project. And with that, say thanks and take any questions.